Hello, folks.
Hello, folks.
Wow. Welcome to the next episode of Lagrangian Mechanics. Today, we're going to give you a full crash course on Lagrangian Mechanics. We're going to discuss everything from moving inclined planes to spherical pendulums to every kind of crazy system you can think about. So, today, I'm excited to bring my guest, and my guest is none other than the only Suborno Isaac Berry. So, let's take a look at what we have to say. So, Suborno, can you please give us a brief intro to Lagrangian mechanics? Tell us a little bit about what it is for beginners.
Lagrangian mechanics is an alternative to Newtonian mechanics, mainly based around the quantity of the Lagrangian, which is quantified as the kinetic energy minus the potential energy. With like Newtonian mechanics, you can find the equations of motion of a system by using something called the Euler-Lagrange equation, which is a partial derivative of L over with respect to x is equal to the derivative with respect to time of the partial derivative of the Lagrangian with respect to x dot, which is the derivative of x with respect to time. So that dot notation is something you're going to have to get used to.
Right,
So
absolutely.
the Lagrangian mechanics over Newtonian mechanics are that even though it has slightly harder mathematics, can be applied to a lot more scenarios, such as thermodynamic systems, relativistic systems, and even quantum mechanical systems, making it the leading system of mechanics that most physicists use today.
Yep.
It can also be used to analyze seemingly chaotic systems that would be either very difficult to analyze with Newtonian mechanics or impossible to analyze with Newtonian
Okay,
mechanics.
great. So thank you for your intro. I'm just going to highlight some comments from our viewers live. We have Samim saying congratulations, not sure for what. And okay, so let's get started with our physics and math. So I'm going to share my iPad screen and you let me know if you can see it. So here's my iPad. Do you see it?
Yeah, no.
You should be seeing F equals ma on the iPad.
Yes, I do.
Okay, wonderful. So the
Well, we're
first,
not going to be using F equals ma anymore.
right, but actually the first objective of our lesson today is going to be showing that we can indeed recover F equals ma from the Lagrangian. So let's take a look at how we can do that. So let's first write down the Euler-Lagrange equation. Can you tell me what the Euler-Lagrange equation is, please?
Partial L
Partial L
with respect to x
with respect to x.
is equal to
Yep.
time derivative
The time derivative.
of partial L
Partial L.
with respect to x dot,
Yep.
which is the time derivative of x.
Let me just stop you right there. We have some folks saying, thank you for your time. Isaac Watkins, you're welcome. Congratulations, Jakir Hussein. I want to meet you. That's not going to happen. And Barry Science Lab. Thumbs up from Neswester Pathaw. And Rock On says Tutul. Okay, so we've got our Euler-Lagrange equation. And from this, we can get the equations of motion for any Lagrangian compatible system. But first, we're going to start with a very simple system, and that is a particle that is moving in one dimension and it has an arbitrary potential. So Bruno, can you tell me what the Lagrangian would be for such a system?
Well, it's the kinetic energy, which can be quantified as half mv squared for most systems.
Okay, half mv squared. Yep. I'm
And
going
then
to
we don't
highlight
really
these are
know.
commons. Okay.
And as he said, the potential is arbitrary, so we don't really know what it is. So we'll just call it some function v of x or u of x.
Exactly. Now let's plug this into our Euler-Lagrange equation. What am I going to get on the left-hand side?
Well, you're going to get partial L over partial x. You're just going to get minus u prime x because
Right.
U is the only thing that is a function of x.
Absolutely. And what am I going to get on the right-hand side?
Well, kinetic energy is a function of x dot, also known as v. Can you replace the v with an x dot really quickly?
Sure.
So then that gives us a ddt, just like that really quickly,
ddt
of mx dot,
mx dot.
which would be mx double dot.
And how did you get mx dot, by the way?
Well, we just take the derivative with respect to x dot. So the derivative of x dot squared is just 2x dot, and 2x dot times half m just gives us mx dot.
Absolutely. So this is the equation that we end up with at the end. Mx double dot is equal to minus the derivative, the spatial derivative of the potential. Does this
Yep.
look familiar?
Yep, because x dot dot is actually the same thing as acceleration, a. So it really gives us minus u prime of x is equal to ma. And now you might be like, what is u? What is u? Oh yeah, you see that nabla symbol that looks like an upside down delta?
Yep.
Yeah, that's another way of expressing the derivative of a function.
Yeah.
So anyway, think about gravitational potential, for example.
We have a question from Galaxy Bidan, says, can you tell from second step? And the answer is no. All right, let's keep going.
What did he mean by that?
I'm not sure. So the second step, Galaxy Bidan, I think you're asking about this step right here. All we did in this step is we plugged in the kinetic and potential energies. And then we just proceeded with the Euler-Lagrange equation. So it seems our guest is fascinated by other topics than physics, so we'll leave him to that.
This is a huge cut on my arm.
Okay, we're on live. I don't think that's appropriate. So
yeah, I know.
Do you want to keep explaining how this is equivalent to Newton's second law?
Yeah, potential. The ball. The force is just the derivative of potential. Don't believe me? Well, what's gravitational potential? mgh, right?
Right.
Now take the derivative of that with respect to space. That gives you mg.
Right. And exactly. And Galaxy Bidan says x is a variable. And indeed it is, because the horizontal position is changing, right? So there you go. That's the answer. Okay, so we're going to move on to our next system, which is a simple 2D pendulum. Okay. A pendulum is nothing more than a rope that has a mass attached to it in a gravitational field. And what we're going to do is analyze the motion of that mass as it moves.
Wait, I have a request.
Sure.
Is there a way you can analyze a system where the string itself has mass with Lagrangian mechanics?
Yes. In that case, you would have to model the string as an arbitrary number of springs that are connected together. These springs would be connected in series. And as a result, their effective spring, what is it called? The effective spring constant for springs that are connected in series is going to be 1 over k effective is 1 over the spring constant of the first spring, 1 over the spring constant of the second spring, just like resistors, adding up resistors that are in parallel. So if you want to find the effective spring constant, this is how you would go about doing it. And then once you find that, you can model the series of springs as a rope. So that's the answer to your question. We have a question from Sharayan Zone, who says, I can learn and understand a lot from your videos. And Taki Tassan Drubo asks, if U is internal energy, which is converting to force, then why is it negative? Okay, that's a very good question, Taki. So, Subarna, do you want to try answering that question?
Well, I'm not a very good candidate for answering that question. But imagine, for example, a ball falling. It can be analyzed basically the same way: half mx dot squared minus u of x. And so its equations of motion would just be mx dot dot equals minus u prime of x.
Okay, now, that's fine.
One second. When we have a ball falling, then the only potential that we really express interest in is the gravitational potential, also known as mgh. So mx dot dot is going to give us minus mg, the derivative of minus mgx with respect to x, which is just minus mg.
That's all great and fine. That's a mathematical reason. Yeah.
Yeah. So can you explain the intuitive reason?
That's a mathematical reason. I like that explanation. Here's another way that might help you understand, Taki. So here's how we can reason about it. The way I like to explain why the potential has a negative sign is I look at two charges that have positive signs, right? Two protons, right? And they
Mhm.
experience a force, K, Q1, Q2 over R squared. That's the Coulomb force. But what is the Coulombic potential for this electric system? Well, the
But
Coulombic potential is K Q1 Q2 over R. But check out what happens when I take this thing's derivative. The derivative of the potential should give me the force experienced by these two charges. But it does give me that, but it comes at a cost. And that cost is a minus sign.
minus.
And so to fix
But
that
that's a
cost,
mathematical reason, not a real reason.
to fix
No?
that, I multiply by a negative, hence making the force positive, which it
But
should
that's
be.
a mathematical reason, no?
That's all I know. So we're going to move on to the next system, which is a pendulum, a simple pendulum. We have a comment from Galaxy Badan who says a combination of spring constants is a good analogy with a capacitor. That's exactly right, Galaxy. In fact, if you add up capacitors in series and parallel, that's a very good analogy for adding up springs in series or parallel. In fact, here is how two parallel springs would add up. If you had two parallel springs with spring constants K1 and K2, so Borna, what would be the effective um, spring constant if not K1 plus K2, right? They just add up. But if you have two springs that are in series, then you'd have to add them up like
Yes,
resistors in parallel.
just like resistance. Yeah, okay.
And Galaxy Badan also says you're doing work against the electric field, which is another way to explain the negative sign in the potential. So let's move on to the pendulum, the simple pendulum. And I'm going to let our host here, Saborno, guide me through what to do. So why don't you tell us how to get started, Saborno? What should I do to find the equations of motion?
All right, first of all, can you write down the Lagrangian equation?
You let me know what this is.
Huh?
Tell
Oh,
me what
that's
it is.
like the string L.
Okay, but what is the Euler-Lagrange equation?
Oh, sorry. Partial L with respect to x
Mm-hmm.
is equal to the time derivative of partial L over partial x dot.
Okay, if our host would brighten up, then we'd continue this session. So let's take a look at what this equation tells us. So
Yep, I can do it, sure.
the first thing we should do is write down the Lagrangian, which is the kinetic minus the potential. So why don't you tell us what that would be?
The kinetic energy can easily be expressed as half.
Mm-hmm.
Actually, wait a second. Since we're dealing with a two-dimensional system,
Yeah.
then x and y can be expressed as functions of theta. So what we're going to do is, you can resolve that. How can you express the x coordinate? Can you tell me in terms of theta?
Indeed, I can. Indeed, I can. So let's take a look, shall we? Let's say I draw over here. Oh, I can't draw maybe, but maybe I can use this. So over here, this can be our y, and over here, this can be our x. So let's see what that would be. What are those coordinates? So,
Why don't you tell me?
That's going to be x is L sine theta, and y is negative. It's in the negative direction. It's going down. Of course, we can choose our coordinate system however we want, but these are the coordinate systems that I'm using. So our y coordinate is going to be minus L cosine theta. And so our next step is, as part of the Lagrangian, we need to evaluate the derivatives of our coordinates. So let's evaluate the derivatives of x dot and y dot, if only our host would be so gracious as to tell us.
All right, so the derivative of that is, with respect to time, is just L theta dot,
L theta dot.
sine, cosine theta.
Mm-hmm.
And y dot would be L theta dot sine theta.
L theta dot sine theta. So what is our kinetic energy T?
So our kinetic energy is just going to be, well, half m,
Mm-hmm.
and then v is just our, x dot squared plus y dot squared.
Yeah.
And that's equal to half m.
Half m. Oh, we forgot to add an additional parameter, which is that the mass of this ball is m. Okay, keep going.
Oh yeah. So m, L theta dot cosine squared theta.
Really?
Yep.
Okay, well, I guess we don't have to put squares on these.
Oh, shoot. Sorry. I
Okay,
forgot. Plus L squared theta dot squared
plus L squared theta dot squared
sine squared theta.
sine squared theta. Now we have an individual, a commenter, who is asking us to respond to their comments. Tartil Online Quran Learning, thank you for your comments. Indeed, we appreciate it. So let's keep on going. How can we simplify this? How can we simplify this?
Well, you can factor out L squared theta dot squared, and once you do that, you'll notice you have left in the parentheses sine squared theta plus cosine squared theta.
And what is that?
They also know that that is equivalent to 1.
Exactly. So what is our kinetic energy reduced to?
Kinetic energy is just going to be half m L squared theta dot squared.
Exactly. And now we just have one more component to figure out, and that is the potential energy. What should our potential energy be? Just generally, what's the equation for potential?
The equation for potential energy, I'm pretty sure, is equal to, well, in this system, we're only concerned with gravitational potential energy. So we'll let it be not exactly mgh, but I guess mgy or
mgy. Okay, exactly. Now, that's the gravitational potential energy. But wait, what is y? If not minus L cosine theta. So what is our potential energy become?
Minus mg L cosine theta.
Okay, now you tell me what our Lagrangian ultimately is.
Well, it's going to be half m.
Someone says the sound has gone, but actually I still hear our sound. So we should be fine. Okay, so half mv squared, but of course we've gotten our kinetic energy right here. So I can just write that down. And what about what should I write for the rest of it?
Plus.
Good. I was waiting to see if you made a mistake with the sign. Okay. Wonderful. We have our equation, our Lagrangian for a simple 2D pendulum. So now what we're going to do is, sorry?
Now we're just gotta solve it using the Euler-Lagrange equations, and I think I can direct you through how to do that.
Okay.
Our variable here is theta, and we don't have to think about L because L is a constant. Theta is constantly changing.
Okay, so let's do it. What should I write down?
Well, first of all, in your Euler-Lagrange equation up there, you see it?
One of our commenters is saying our sound system has gone, but we actually hear our audio pretty well. So I think the sound should be fine. Okay, keep going.
Anyway, you see your Euler-Lagrange equation up there?
Yeah.
Now replace all the x's with theta because theta is our real variable here.
Okay, so I'm going to have partial L partial theta is equal to d dt partial L partial theta dot. Is that correct?
Indeed it is.
Okay.
So partial L partial theta is going to be...
All right. So our host is suffering from casualties. So let's continue. So partial...
Okay. It gives you minus mgl sine theta dot.
Theta dot?
Yeah.
Really?
Oh shoot, yeah. We're not differentiating with respect to time. I'm sorry, I made a mistake.
Okay.
It is equal to ddt because I'm too lazy to take the time to read it right now.
Okay.
of ml squared theta dot.
ml squared theta dot. Okay.
And now I can take the time derivative of that.
Okay.
So it just to be ml squared theta dot dot.
Okay. Is equal to?
Minus mgl sine theta.
So let's solve for the equation of motion for theta double dot. What is that?
Well, we can cancel out the m and l on both sides.
Okay, so cancel out the m and the l on both sides. What do we get?
L theta dot dot.
Theta dot dot is equal to minus
G over L sine theta.
Precisely. And this, ladies and gentlemen, is the equation of motion for a simple 2D pendulum. And we have Galaxy Badon says, guys, you just keep on going and take a break after you acquire an expression. During that break, I would like to ask questions as being skeptically questioning species. Sure, Galaxy Badon. Okay, let's keep on going. Now, some users in the comment might rage. They might say, why do you have a negative sign? And to that, my only response is that it's a symptom. It's a symptom of the coordinate system that you choose. So if you choose a different coordinate system, you might end up with a plus g over L. But at the end of the day, this is the fundamental equation of motion for a simple 2D pendulum. Now, what steps can we take to solve this second order differential equation? Any ideas?
I'm pretty sure we can't solve it with
exactly. We cannot analytically solve this system, but we can do something nice. We can say, you know what if the pendulum doesn't move that much? Is there any approximation that comes to mind for things that don't move very much?
Well, sine theta, the first order Taylor approximation of sine theta is just theta.
Exactly.
Yeah, if you really want to get fancy, then you could do theta minus theta cubed over 6. But nobody in physics goes that far.
Right. And this is coming from a guy who wrote a paper on Taylor expressions. But anyway, so this is great. We have an equation, and our guest has just suggested that we use the Taylor approximation that sine theta is approximately theta for small values of theta. Okay, so let's go ahead and exploit this expression, this approximation. So then our equation of motion becomes theta double dot is minus g over L theta. Okay, and I'm just going to delete the minus sign so that I can really expose what's going on here. What we have right here is not just any second order differential equation. We have an exponential second order differential equation, meaning that the solution to this differential equation is nothing more than e to the square root of g over L t. Okay, another way that I can say that is instead of theta is an exponential, I can also write it as cosine of square root of g over L t. And now I'm going to show you that this is the case. Okay, which one do you want to choose? They're both the same, but I'm going to ask our guest which one he wants to choose.
Well, the easy way out is to...
Subarna, we have a question from Navye Anand who asks, what exactly did you submit to the Annals of Mathematics? Now, I know you can't exactly say what you submitted, but can you just give us the title of your paper or a very brief one-sentence summary?
Confidential.
Okay, moving on. Galaxy Bidan asks us, why don't we take modules so that negative becomes positive? Not sure what modules are, but maybe you meant modulo, but that's modular arithmetic. Anyway, so let's move on. Which version of the solution would you like to proceed with? The exponential or the cosine? They're both the same, but whatever you want.
I'll do the exponential version.
Okay, can you stop doing that?
No, like my lighting changes when I put my hand up versus when I keep my hand down.
So what is theta dot if we choose the exponential version?
Well, theta dot is just going to be root g over L times t.
Root g over L times t? Really?
Oh, times the original theta.
Okay, which is this. And what is theta double dot?
Well, it's just going to be G over L times. Wait, you forgot the T there for theta dot.
Really? Is there
Yeah,
supposed to be a T?
I'm pretty sure. Oh wait, no. Oh, because we're differentiating the time.
Right.
Yeah, I know. So we get G over L times theta.
We have a question from Quick Maths TV. Did he submit a paper for publishing? Suborno, would you just like to say what stage of the peer review process your paper is under?
I have no clue, but I did submit it.
Okay, it's under peer review. We'll leave it at that. So let's keep on moving. We have G over L times this. Now, can you not do that, our host? Can you explain what?
And G over LT is also the same as theta. Now, it would be much more complicated if we use the second order Taylor approximation, which is slightly more accurate. But yeah, that's that.
Yeah, and it's amazing. We've gotten the equation of motion for a pendulum. Now, you might say, okay, big deal. Who cares? Who cares? The answer, every individual in the 18th century. And this is why. People in the 18th century were trying to figure out what G is. You see, Newton didn't actually know that G was 9.8. So people had to figure out what the actual value of G was. And so here's how they did it. This square root of G over L, this right here, is the angular frequency of our simple 2D pendulum. So omega is square root of G over L. But if omega is square root of G over L, then what is the period?
Oh, sorry. What?
Well, omega is 2 pi times the frequency. Would you agree with that?
Yes, I would.
And so what is frequency if not 1 over the period? Okay, so what can we say? What is omega in terms of the period?
2 pi over t.
Okay, and what did we just figure out omega is from our derivatives?
We did figure out that theta dot is, I'm pretty sure, root G over L.
You mean omega is root G over L?
Oh yeah, root G over L.
So
wouldn't it be G over L theta?
This is just omega. Remember that theta double dot is G over L theta, and so theta is e to the angular frequency times time.
No, but theta dot is root G over L theta, no?
Yeah, it is, but we're looking at theta, right? What is your question exactly?
No, I mean, before you said that omega was root G over L theta, and now you're saying it's just root G over L. Where's the theta go?
No, see, theta dot is this, right? Would you agree with what we have right here?
Yeah, and that's equivalent to root G over L theta, no?
I don't see what your confusion is. Our angular frequency is this, right?
1 second, okay.
Yeah.
Okay. You see that second equation, theta dot equals?
Theta dot equals, okay.
Can you not rewrite it as omega equals?
Now theta dot, you could technically, well, theta dot is usually d theta over dt. Actually, it's always d theta over dt, which you can write as angular frequency, but that's for like circular motion. Here we're analyzing the pendulum. We're not going to replace theta dot with omega.
Then okay. What is the purpose of putting theta dot?
The purpose is taking the time derivative so that we can take it a second time and show that theta double dot is equal to G over L times theta.
But if it's not an example of circular motion, why do we get equations of circular motion when we keep the Lagrangian?
What do you mean?
Never mind, I'm done. Okay, just continue.
Because the pendulum doesn't exactly execute a circular trajectory.
Then why do we get equations for things like angular velocity and acceleration?
Does spring execute a circular motion?
Oh.
Does the spring have angular frequency?
It does have a frequency.
It has an angular frequency, which is defined as 2 pi times its regular frequency.
Yep, I got it. Geez.
Right? From simple harmonic motion.
Yes, I got it.
Right. Any object that executes a simple harmonic motion has these properties. So, that being said, but very good question. That raises the point that this right here is our angular frequency omega. And actually, Galaxy Bedan pointed out, the period is what we're going to get to. So, Saborna, what is our angular frequency? Just take a look at this. What is our angular frequency for this system?
It's root G over L.
Root G over L. From this, can you tell me what the period of a pendulum is? Derive it.
We do know that omega is 2 pi f, or 2 pi over t. So that means t equals 2 pi over omega. So it's 2 pi root L over g, which is one of the most famous equations in simple harmonic motion.
There you go. There you go, ladies and gentlemen. That's actually exactly what Galaxy Bedan posted in the comments. And also Anaruda Divadaldi, sorry if I'm mispronouncing your name, asks, sine x also equivalent to x for x belongs to 0 to 30. Okay, good to know. I actually thought it was between 0 to 15, but okay, good to know that it's valid for more.
Oh, wait, you want to know something cool?
Yeah.
Right. Did you know that the second order Taylor approximation for sine of x is basically valid until x equals pi over 2?
Wow.
Yeah, so that means that it's basically an accurate representation of any pendulum moving. And the third Taylor approximation is basically completely accurate after pi x equals pi over 2. So that means that using the second or third order Taylor approximation, you can very, very accurately analyze even large angular motion, even though the differential equations would be very chaotic.
That's kind of nuts. That's good to know. But actually, in classical mechanics, we never traditionally go above the first order term. I mean, if you want to write a paper, then sure, you can start with the second order term. I've actually seen someone do that. But anyway, let's move on to. Thank you for the suggestion, though, host. So guest. So our next system is none other than a generalized version of the 2D pendulum, and we're gonna have so much fun with this. Now, our guest, would you like to tell us what this system is? Saborna?
I think it's called a spherical pendulum.
I think so too. So let's analyze the behavior of the spherical pendulum, shall we? So let's get started with the basics. The first thing we're going to need to do, I don't think what you're doing is, okay, let me just stop the live.
Okay, I'm so sorry.
No, that's fine. Let me stop the live, and yeah. Unless you want to continue.
I'll continue.
Okay.